Alright guys, in this section we are going to talk about a new way to call coordinate points. So you're used to what's called the Cartesian coordinate system or the rectangular coordinate system, and that is you have a horizontal distance x, a vertical distance y, and you can plot points using the horizontal and vertical components of that point. In this system we are going to use, our points are going to be r comma theta, where r is the distance from the origin. And in this case, it's called the pole. So obviously, this looks a lot different than an xy coordinate plane. You should look. This should look familiar. It should look like the unit circle because we're going to use angles. But we have a bunch of these rings going out, and not just one circle. But again, r is going to be the distance from this center point to wherever that point is, and theta is going to be the angle between the x-axis, or in this system it's called the polar axis, which is just going to be straight out to the right. The distance between that, the angle between that and where the point is located. So let's say I have a point up here. That point, the r is going to be, again, the distance from the middle. So I'm just going to count how many rings we go out. So that is on the fourth ring. So my r value is 4. And theta is what angle is that located at? And that would be at pi over 3. Okay, so that is a different way to call coordinate points. And so you're going to want to reference your unit circle. If you have that, if you don't have that, hopefully you can Google search a unit circle to help you with those angles if you don't remember them. But anyway, it's just how far out from the center. So what ring is it on? That's the way I like to think about r, is the ring. And then what angle. So we're going to practice graphing a few of these points. And there are some things that come up that make it a little bit more challenging. So we'll look at those as they come. The first one is the point 1 comma 3 pi over 4. So I like to start at the angle, actually, and then go back to, okay, then what ring am I on? So A, the angle is 3 pi over 4, so that is the middle one in quadrant 2, and we are on the first ring, so this right here is going to be point A. Point B is 3 comma negative pi over 6. So if you remember, when we go in the counterclockwise direction, those are positive angles. I can go in the clockwise direction that same distance and get those negative angles. So what that means, if you forget this, what that means is that since this is the angle pi over 6, that's just going this distance, positive direction. If I go that same distance in the negative direction, this is going to be the angle negative pi over 6. You could also, if you remember, you could find the coterminal angle of that. So what you could do is simply add 2 pi to that, which would give you 11 pi over 6. And then you would know where that's located. And then we're on the third ring, so I will go out to the third ring and plot that point. That is point B. C is 3 comma 3 pi. So again, third ring, 3 pi. Remember, all the odd numbers of pi are located over here on the left. That's 1 pi, and then 3 pi, and 5 pi, and so forth. All the even numbers of pi are over here on the right. So 3 pi is going to be straight out to the left on the third ring, which is going to put me right here. And the last point, that's C. And the last point is negative 4 comma pi over 4. So this is a little bit tricky when we do negative r values. So pi over 4, you should know, is located here in quadrant 1. It's the middle line in quadrant 1. But the r value is negative 4. So think about that as kind of like your positive axis now, where pi over 4 is located. So if it were 4, I would simply just be right here, right? But it's not 4. It's negative 4. So I want to go directly across the circle from that out to the fourth ring, and this is going to be the point D. Okay, so whatever that angle is, start with that, and if r is negative, go directly across the circle, that distance from that angle. Okay, so this next part talks about how we can have a lot of different names for one point. So in the Cartesian system, what you're used to with x's and y's, there's really only one way to call a point. So if I say the point 2, 3, you know that means go horizontally 2, vertically 3, and plot that point, and that is the only point that will be in that location. In polar coordinates, because you know things like coterminal angles, and now that we know how negative r's affect things, we can actually end up in the same exact location using a lot of different coordinate points. So I'm going to go ahead and plot the point 4 comma pi over 3, which is right here. Okay, so that's on the 4th ring at the angle pi over 3. The question is, it wants us to find 3 other representations of that same point. So I'm going to do some different things here. One, I could keep this as 4, and then all I need to do in order to get more representations of that is I need to find a coterminal angle to pi over 3. So if I just simply take pi over 3 and I add 2 pi to it, that's going to give me a coterminal angle, which we know is in the same location, and therefore it would be the exact same coordinate point. So if we take pi over 3 and add 2 pi, just remember when you do that, you need to get a common denominator. So if I add 2 pi to that, that's going to be adding 6 pi over 3, so that's going to be 7 pi over 3. That's one way I can do it. Another way I can do it is I could use negative 4 instead of positive 4. So if I'm going to use negative 4 as my r value, that means I don't want to start at pi over 3 because negative 4 would take it directly across the circle. So I actually want to start down here at this angle, so that when I go directly across negative 4, I'm going to end up at that point that we have located. So that angle is going to be 4 pi over 3. So if I use 4 pi over 3 with a negative 4r value, that's going to take me across this circle, and that's going to end up in this exact same location. All right, and then since I know that, I can continue to use negative 4, and I could just find coterminal angles to that. So I could take 4 pi over 3, and I could add 2 pi to that, and that's going to give me some more coterminals with 4 pi over 3 that then if I use negative 4 as the r value, will map over to that same coordinate point. So again, adding 6 pi over 3 to that, that's going to put me at 10 pi over 3. Now, I've just given you 3 different ones. Again, all of these points that we have listed are all going to be in that exact same location. There are infinitely many. You could keep adding 2 pi, you could subtract 2 pi. You could, when you subtract 2 pi, you could introduce some negative angles there that may make more sense than some of them that I wrote. But there are a lot of different ways I can call that point, and that's kind of unique with the polar coordinate system and something we can't do with Cartesian coordinates. Okay, so this last part talks about how we can take a coordinate point and call that same exact location in terms of rectangular coordinates, x comma y, and polar coordinates, r comma theta. And it will be the exact same location. And these formulas help us do that. Okay, so the idea is if I had some point out here somewhere, with the rectangular system, again, what we call this is we call this distance x, and we call this distance y. And if I use a horizontal distance x and a vertical distance y, that's going to give me whatever that coordinate point is. Okay. Well, with polar coordinates, what we're concerned about is the straight line distance, right? That was called r, the straight line distance from the center to where that point is located. And then what was the angle theta inside here? What was the angle that gave us that point? And that would give us that exact same location. Okay, so if we think about right triangles here, hopefully these conversions are going to make sense. The x coordinate is this horizontal distance. So if I think about, really if I just think about SOHCAHTOA, this is going to make sense, right? So the cosine, if I just think about the cosine of the angle theta, that's going to be the adjacent side divided by the hypotenuse, which would be x over r, which then if I multiply the r over, that gives me x equals r times cosine theta, which is going to be what this is here. Okay, same exact idea using sine instead of cosine is going to give me this conversion that the y-coordinate is simply just going to be r times the sine of theta. Okay, so that's if I have the r theta, the polar coordinate, r comma theta, and I want to go to rectangular coordinates. How do I get those x and y's? And I just simply do r times the cosine of theta, r times the sine of theta, and that will give me x and y. Again, if I start with x and y now, again, these should make sense using what you know about right triangles. This should look very familiar. This is just the Pythagorean theorem, right? So if I have x and y, those are like my side lengths of a right triangle. To find r, I just use the Pythagorean theorem. R squared equals x squared plus y squared. And then the tangent of theta is going to be opposite over adjacent, so y over x, and that would give me this. Okay, so the easy conversion, I think, for most people is to go from rectangular to polar. And so, I'm sorry, from polar to rectangular. So if I have a polar coordinate, 4 comma 2 pi over 3, I want to find the rectangular coordinates. I know that my x is simply going to be 4 times the cosine of 2 pi over 3. And I know that my y-coordinate is going to be 4 times the sine of 2 pi over 3. Okay, and so 2 pi over 3, the cosine of that, the x-coordinate there is negative 1/2, which gives me an x-coordinate of negative 2 when I multiply that. And the y-coordinate at 2 pi over 3 is root 3 over 2. And so if I take 4 times the square root of 3 over 2, that's going to give me 2 square roots of 3. And so what we found is that the xy coordinate point, negative 2 comma 2 square root of 3, that coordinate is in the exact same location as the polar coordinate 4 comma 2 pi over 3. Another way to do that really quickly is if you just look, if this is a unit circle angle, it's very easy. If this is a unit circle angle, all I really need to do is find the coordinate point at that angle, which would be negative 1/2 comma root 3 over 2, and then simply multiply by my r value of 4, which is what I did individually there, and that would give me those new coordinates. Okay, and then the last part is going the opposite way. So if I have an xy coordinate point to negative 2, and I want to find the r and theta. Okay, so to find the r, we're going to use the Pythagorean theorem that r squared is 2 squared plus negative 2 squared. So r squared is going to be 4 plus 4. So r squared is 8. Take the square root. R is going to be, now technically I would have positive and negative. Square root of 8, I'm going to simplify that into 2 square root of 2. Okay, so I've got two different r values there. And then for theta, we're going to say that the tangent of theta is equal to y over x, so negative 2 over 2. So the tangent of theta is equal to negative 1. And then we want to do inverse tan, right? So theta is going to equal the inverse tangent of negative 1. So remember, the way you do that, to find the angle, you have to use inverse tan, and that means at what angle is tangent negative 1? And you should get two of these, right? So theta is, tangent is negative 1 at 3 pi over 4. And also at 7 pi over 4. Okay? So I have two thetas, and I got to match them up with the two r's that we got. And the way you do that is to think about where this coordinate point is located. So 2, negative 2, that's in quadrant 4. So if that's in quadrant 4, I'm going to pick the angle that's in quadrant 4, which is 7 pi over 4, and that's going to get the positive one of these. So my r comma theta is going to be positive root 2 over 2, comma 7 pi over 4. And that is it.